Yeah. So in today's lecture, we are just going to learn about transformer theory and its operation. Okay. So an ideal transformer is something like this. You will have a magnetic core. You will have an coil on one arm, and which is known as the primary coil, where you have a source connected, and you also have a secondary coil wherein you have a load which is connected here. Now the Lentz law is applicable to both the coils. Okay, so here if you apply a voltage E, right, so it will cause a magnetic field which will be defined by this formula. So E N d phi by dt, right. On the other side, we are not applying a voltage, but there is a d phi m by dt, so that because of which an voltage will be induced into the secondary. So when we apply a primary a voltage in the primary coil, there will be an flux, okay, and that flux gets linked to the secondary coil, and then voltage will be induced into the secondary coil. Okay, so that is how we are able to drive a load. Now here few things, very important things to understand is, suppose I apply a DC voltage out here, a DC current will flow in this coil, and that will establish an fixed flux. Okay, so in that case, there will be no d phi m by dt. Okay, there will be no rate of change of flux. There will be a fixed flux, and no voltage will be available at the secondary output. So this transformer is only applicable for AC circuits. Okay, you apply a time variant signal in the primary, which will cause an variable flux here. Okay, not a constant flux. So a variable flux, that means d phi m by dt has to be finite. It cannot be a constant. So that can happen only for an AC signal. So that d phi m by dt will induce an voltage in the secondary. So that is how we are able to drive an load. So this is known as the primary coil, this is known as the secondary coil. And also not necessarily we have the same number of coils in the primary and secondary. Generally it will be difference. There will be a difference of number of coils, and that is the very purpose of a transformer. We'll see in the next slide. Now what does this change of number of coils on the primary coil and the secondary coil, how is it going to change the voltages in the primary and the secondary, that we'll see in the next slide. So if I try to apply this Lentz law here and here, you will say the E primary is N1 d phi m by dt, and here in the secondary it will be N2 d phi m by dt, where N2 is the number of coils of the secondary and N1 is the number of coils in the primary. So if I divide these two equations, I will get E primary divided by E secondary is equal to number of turns of the primary divided by the number of turns in the secondary. So if I have a number of turns of the primary larger than that of the secondary, then I can have, and I will have a secondary voltage which is less than the primary. Similarly, so that I can step down the voltage. So these kind of small transformers, you will find it in your mobile chargers and your laptop chargers and all, where you have a 230 volt supply. So you will have to rectify that. You require a DC voltage which is of only 5 volt or 6 volt. So the very first thing we need to bring down that 230 volt to around 10 volt or something, and then 10 volt AC, and then rectify it into a DC voltage. So these are they are known as the step down transformers, which you will find it in most of your mobile chargers and laptop. And also in the transmission line, we spoke about like when we are transmitting a signal from place A to place B, it is if for a given power, if the voltage is very high, because P is given by Vi. So if the voltage is very high, I will be less, so the transmission losses will be lesser. So generally from the source it will be few kilovolts of supply which will be transmitted from place A to place B, and as you come close to the load, like when it reach, there will be step down transformers at every junctions, and then by the time it comes to your house, it will be 230 volt. So when I am transmitting between two major cities, maybe I will transmit only in kilovolts, okay, and when I have to transmit from the nearest sub, so that voltage will come to the substation where it will be stepped down to say finally to 230, and that will be supplied to the house. So these are all the applications of transformers. Now for the next two slides, when we are going to discuss the philosophy of transformers. So this equation, EP by ES is equal to NP by NS, we are going to use this, but these are some of the assumptions for this equation to be applicable. Okay, first one is all flux produced by the primary coil links to the secondary. So this is an ideal transfer, that may not happen always, right? So you have to take care that whatever is the flux which is produced by the primary coil is linked to the secondary. So no core loss due to hysteresis or eddy currents. Okay, this is the core, right, in which the magnetic field flows. So there has to be there should not be any hysteresis loss. Okay, now what is hysteresis? So like to generate a certain magnetic flux, you give certain voltage, and when you remove that voltage, okay, some amount of magnetic field residual will be there in that core. Okay, so that is known as hysteresis. Okay, and then you have to give a certain negative voltage to remove that hysteresis. So in that process, some energy gets consumed in the core. Okay, that is known as hysteresis loss. Similarly, whenever there is a magnetic field associated with a metal, it will induce some currents in that metal. They are known as eddy currents. Okay, because in that will act like a coil. Even a metal sheet will act like an coil, and since the resistance is very less, huge currents can flow and cause heat. Okay, so and it will dissipate energy. So these are known as the core loss. Okay, one is due to hysteresis, other is due to eddy current. So for an ideal transformer, we are assuming that there will be no hysteresis loss and no eddy current losses, and no power losses. No power losses means we are assuming that these coils, primary coils and the secondary coils, they don't have any resistance. It is pure inductor, so that the entire there is no I square R losses. Okay, and the permeability is infinite. That means there is no saturation of the core. So suppose we give an as we keep increasing the voltage, the magnetic field will keep increasing in the core. It is assumed like that. The core doesn't get saturated, but in all practical metals, after some time it cannot, when all the ions in the magnet gets aligned in the particular direction, it cannot further increase the magnetic field. Okay, that is known as core saturation. So we are assuming that in this particular, in an ideal transformer, that doesn't happen. Windings have zero resistance, and no current is required to magnetize the iron core. Like the moment you apply a voltage, the core gets activated. Okay, magnetized. So we are tell me, Gagan, you have some doubts?
So could you repeat the saturation part again?
Okay, yeah, okay. The thing is, when I am giving an current into the coil, when I am applying a current which is passing through the say certain current, so zero current is flowing, slowly the current is increasing, the flux also will increase. Okay, so if the current keeps increasing after a certain amount of time, value of the current, okay, when the the amplitude goes to an adequate level, what happens is how is a magnetic field created within this core? Because there are ions, floating ions available in the core, they all start getting aligned. Okay, but after some time, all the ions which are available in the magnetic core, they get aligned. Okay, and then the flux cannot increase beyond that value. Okay, so they are known as like ferromagnetic compounds and all. They have limited number of free ions which can get aligned, so they get saturated very fast, whereas steel and all, they have large number of ions, they so free ions, so they will not get saturated very soon. Okay, is it understood?
Got it, sir. Thanks,
Okay,
sir. Got it.
so that is what. As long the relation between the flux and the applied voltage has to be linear. Okay, but practically for a very large voltage, they will the flux will start getting saturated. So we have to take care of that. Okay, so these are some of the assumptions we have made out here, and subsequently we'll remove these assumptions and we'll model the transformer accordingly. So to start with, we'll assume that all those losses are not there. Okay, now this A is known as the transformer ratio. It is primary divided by secondary, so it is also equal to E primary divided by E secondary. So we know E primary is equal to A into E secondary, right? Now the power also, if you see E primary into E primary into I primary is equal to E secondary into I secondary. That is because we are assuming there is no power loss in the primary, right? So that's why whatever is the power, this voltage into this current will be this voltage into this current, because power cannot be created nor destroyed, right? Conservation of power, and we are assuming there is no power available here, no power consumption in the core. So this is the equation which satisfies. Okay, so suppose I am not now if we can so the current ratio also. Okay, let me first discuss the current ratio. So the current ratio I primary divided by Is will be 1 by A. If you see here, if you replace the E power by V into V divided by I, so you will get this ratio, this. Okay, I primary will be lesser if the will be 1 by A. That means if the voltage is high, the current will be lower. Okay, so this is the third equation. So these are the three fundamental equations. And now physically, let's try and explain and try and understand what happens in a transformer. Suppose I have given some voltage out here. All right, there is a coil out here that creates a magnetic field out here, right? And the secondary is open out here. So if as long as the secondary is open out here, so this magnetic flux creates an opposite magnetic opposite voltage in the primary coil itself, so that no current will flow here. Okay, but the moment you connect an load out here, okay, proportional to the current which is flowing in this coil, okay, and magnetic field will be created, and that magnetic field will create an voltage out here, okay, which will in fact reduce the self voltage, the back EMF which is generated by this. So a current will start flowing here. Okay, so initially when there is no load connected here, only primary, there will be some current will start flowing, that will create a magnetic field, and that magnetic field is known as the back EMF. Okay, that is known as the back EMF. So that back EMF will oppose this voltage which is created here, and so no current will flow. So as you keep connecting load and reduce the resistance here, more current will flow here. So that current will induce a secondary voltage here, and that secondary voltage will reduce the effect of the back EMF, and hence a current will flow in the primary. So whatever is the so the current in the primary will be a function of the current which is flowing in the secondary, and that will be the given by this equation. Okay, so that is how the power gets transferred from here to here. Okay, so that was the physical explanation. Now if you have to see the impedance, suppose this is the impedance of is Z load. Okay, so Z load will be defined by this equation, E secondary divided by I secondary, right? So so now if you see Z in, okay, the Z in is the impedance which is seen into the primary coil here. right, which is E primary divided by I primary. Now E primary, okay, now E secondary divided by I secondary, I can write in terms of in the primary by EP divided by A and A into IP. So which will give E primary. So this A comes in the denominator. You have E primary divided by I primary A square, right? So what is E primary divided by I primary? Okay, that is Z in. Okay, and what is ES divided by IS? That is Z load. I get Z load is equal to Z in into 1 by A square, or Z in, that is the impedance as seen into the primary, will be Z load into A square. Okay, so you will find the impedance as seen into the transformer will be A square times the Z load. Okay, so this is one important equation which you need to remember. Okay, so so if you see if A is no, more than 1, that means if the number of turns of the primary is greater than the number of turns in the secondary, then Z in will be higher than Z load. Okay, so that need not be the case always. You can have an up transformer or a step up transformer or a step down transformer. So A can be greater than 1 or can be less than 1, depending on. If it is greater than 1, it will be known as a step down transformer, and if it is less than 1, it will be known as a step up transformer. Accordingly, these ratios will differ. Okay.
Could you repeat that? If A is less than 1?
If A is less than 1, it will be known as step up transformer.
So how, sir? If A is less than 1,
Yeah.
it means 1 second.
A is primary divided by secondary, right? So the so if A is greater than 1, then the voltage will step down.
Oh, you got it, sir. My bad. Understood.
Correct? Okay.
Yeah.
Okay. This is that. So we take an example out here. We have 300 kilo volt ampere. This is the rating of the transmitter. Okay, a transformer. 300 kilo volt ampere. That means this is the maximum power of the transformer. 2400-120. Okay, that means when you apply 2400, you, at 60 hertz, you will get 120 at the output. So this is the rating of the transistor. Okay, single phase transfer operates at 2300 volts. Okay, now I am not applying 2400, that is the rating of the transformer. I am only applying 2300 on the primary side. Okay, now when I am applying this, it supplies 115 kilovolt ampere to the load and has a power factor. So on the load side, this is the VA and this is the power factor. Now we need to find out the secondary voltage, secondary current, impedance of the load as seen on the secondary side, and impedance as seen on the primary side, right? So the first thing is we need to find A, which is V primary divided by V secondary. So this is the rating of the transformer which is given. So I 2400 divided by 120, I get 20. Now what is the secondary voltage? Secondary voltage is not 120 because we are not applying 2400, we are applying only 2300. So to get the secondary voltage, 2300 divided by A, which this should have been I think 20, divided by 20, so I get 115 volt. Okay, so had I applied the full voltage, I would have got 120. Since I am applying 100 volts lower, I am getting 115 volt here. Now this is VA, this is the power which is being consumed, is given as an 115 kVA divided by 115 and a volt. So I get 1000 amperes. This is K. K stands for 1000, right? So I get 1000 amperes current in the secondary, right? Now now to find out what is the source impedance. Okay, from the I get. So the secondary impedance is this voltage divided by this current. So 115 is the secondary voltage, 1000 amperes is the current which is flowing. So I divide these two, I get 0.115, right? So power factor is again given as an 0.723. So cos inverse of that, which is a minus, so it is a lagging. So 47.3 is the phase angle, that is that. And now that since that is there, so the total secondary impedance will be 0. This is the magnitude, this is the phase, right? Now to find out what is the impedance as seen from the primary side, we need to multiply it with a square, right? And A is 200, A was 20, right? So
A is 20, A is 200 for 4.
yeah, so this has to be 400, right? A square. Correct. A square should be 400. So 400 into this, will it come this? I guess so. Okay. So this is how you find the primary impedance. Okay. So now practical transformers, we said there will be some losses. One is known as hysteresis loss. Okay, what is hysteresis loss? When we say when I am sweeping the voltage, okay, so the field will be set up in the iron core, and when I am bringing that voltage, ideally, say if it is sinusoidal signal, I go to the maximum, I come down to the minimum. Okay, the flux also has to go to maximum, and I have to come to a minimum, but that will not happen because the core will try to retain some amount of magnetic field. Okay, and in the process of retaining it, some energy gets dissipated. Okay, so that is one. And the second one is eddy currents. Okay, so that is one loss which happens. And what is eddy currents? It's a magnetic, if the core can be considered as an magnetic big sheet, okay, that acts like a coil. So when you apply, there is a varying field because of Lentz law. In that core also some EMF gets generated, and because it is a magnetic material or an iron core, the resistance is very less, and that can result in high currents. So high currents will generate heat, and there will be some dissipation of energy there. So these are the two losses which generally happen. Okay, so how to avoid these losses? First of all, to use alloy steels, okay, which don't have hysteresis, okay, and they don't get saturated. So that is one. And then to control the eddy current losses, we use a laminated core. Okay, so in the next slide probably I'll explain what is. So laminated course, there is a slide after one or two slides which will explain what is lamination. Okay, so you can see here, so this is not a single metallic block. This core is made up of large number of thin metallic sheets which are insulated from each other, because each sheet there will be an insulator coat, usually a varnish or a plastic coat above it, and then they are placed. So magnetic wise they act like an single block, whereas for electrical currents they are not a single block, so that will prevent huge currents flowing in these blocks. Okay, so this is known as a shell type, okay, core, so in which the primary and secondary are in between, and then you have the magnetic flow field going like this. Okay, so you have an in between, in the center you have one arm, both the primary and secondary are wound here, and then you have these magnetic fields moving like this. That is known as shell type. You also have a core type. Okay, in the core type you have an single core running like this, and then you have the primary and the secondary. So both these designs, they have their own advantages and disadvantages. You can, if you are interested, you can just Google and find what are the differences between these two, but both are generally used. Both these designs are used. Okay, so like I said, these are the cores which are laminated. So instead of having a thick metal block, you have very thin metal sheets, and there there is a varnish coating on top of this, or they have an insulator coating, and then they are placed together. Okay, so that there is no, that is to prevent eddy current losses in these transformers. Okay. Now the practical transformers, and this is just the primary coil which is shown here. Ideally, if there is no load connected in the secondary, no current should flow there, but there will be small amount of current which will flow in the primary because of two reasons. One is known as IFE. Okay, and this component is because of the resistance in the coil. Okay, and also there will be one, we are modeling it with an inductor, and trying to compute an IM. Okay, that is known as the magnetizing current. That current is because of the inductive reactance, because of the core magnetization. Okay, so these are two. Actually, there is no L and M. Okay, once you apply a voltage, you will find an I0 which is flowing here, right? You will measure this I0. It has and with respect to the applied voltage, you can have a component which is in phase with it and 90° out of phase, and then you can model this and this out here. Okay, so that, and we know the cause of these two is, this is because of the this is known as the core loss component, which is resistance that represents the core loss, and this is an inductance reactance which represents the core losses due to core magnetization. So in any practical transformer, there will be two of these components will be there, and so they will represent the losses which happens in the transformer. Okay. So if I take some example, things will be a little more clear. A 50 kVA 7200-240 60 Hz single phase transformer is operating with no load, with primary connected to 7200 system. It draws 248 watt and has a power factor of this. Okay, so ideally there should not be any power, because secondary is disconnected. There is no load in the secondary, but still 248 watt of power is being drawn. So now the find out the exciting current and its component. Okay, exciting current means these two currents. Okay, current IFE and IM, and the magnitudes of the reactance also, and so this is to be found. Okay, so if you see, this is the power, okay, divided by, this is a phase lag is known as, so you will get if you divide by that, you get 1328.2 volt ampere. So this is the apparent power. Now if I divide it with the voltage, which is 7200, in this case we are applying the entire voltage. In the last case we saw that the full rated voltage was not being applied. Here the full rated voltage is being applied, so I divided by that, so I get the current. Now that is the magnitude of the current. Okay, this magnitude is this magnitude, right? I0. It has got two components now. That is the magnitude. Now cos phi is also given here, right? So this into cos phi will give IFE, into sin phi will give the, so if I go back here, cos phi is also given. This magnitude we first find out, and into cos phi will give IFE, into sin phi will give IM. So that is what has been done here to get the two. Now if you have to find out RFE and XM, okay, either we divide that voltage by this current, or V square divided by power, V square divided by what is this which has been done? Yeah, I think there won't be any square out here, right? Yeah. Okay. So V divided by that current out here, and similarly V divided by this current will be here. Yeah, so first we find out the magnitude of the current and the phase angle. From the magnitude of the current, if you multiply with the sine of that, you get the magnetic component, and if you multiply it with the cos, you get the core loss component. Okay, so if I have to find an RFE, voltage divided by this current. Similarly, if I have to find out XM, it is the voltage divided by this. Okay, is it clear how to do these calculations?
Yes, sir.
Okay. So let me introduce two or three more terminologies. Okay, the one is known as transformer voltage regulation. Okay, so there is something known as an up regulation, and there is something known as a down regulation. So the up regulation is defined as voltage in the secondary when no load minus voltage in the secondary in full load divided by the voltage in the secondary when it is full load. Okay, it is known as voltage regulation up. Generally, if there is no these two components, right, there will be no voltage drop in the primary at all. Then you will find that this voltage regulation is 0. Okay, in an ideal transformer. But when some current starts flowing in the secondary, okay, the secondary voltage will not be the same. Because of the current in the secondary, there will be some current which is flowing in the primary. So that primary current in the will cause the some drop across IR drop and in the primary also. So similarly, there could be some IR drop in the secondary also. So and that is the reason why it will not be the same. Okay, at loaded conditions, the voltage across the secondary will not be same as that of no load. When I say no load, means zero current. Okay, when current flows in the primary as well as in the secondary, the voltage starts dropping. Even though you have applied a constant voltage in the primary, still the secondary voltage starts slowly coming down when the current flows in the secondary. That is because of the drop in the secondary and in the primary, because now it is not an ideal transformer. There will be some IR drops in both in the primary and the secondary. So that is known as regulation up, where the what is the difference between regulation up and regulation down is only thing is the it is divided by a full load out here, and here the denominator is the no load voltage. Okay, so that is two definitions which are generally used in the industry. Okay, so we need to know these two. Okay, at no load, and if you call Vs by Vp as K, okay, that is nothing but 1 by A. Okay, at no load conditions. Okay, then you can write regulation up and regulation down in terms of K also. Okay, so this is not important. So you need to remember these two equations, regulation up and regulation down. Okay, so ideally this should be as close as to 0. That means there is no voltage drop in the primary and secondary, but practically there will be some drop. Okay, so only difference between these two is the denominator. Here it is in a full load and it is no. And what is full load? Okay, that will be defined by the transformer ratings. Okay, this is the maximum current which the transformer can provide, or this is the maximum power which the transformer can provide. So with that we compute the full load conditions. Okay, so that is how. So no load means when obviously there is no that will so when there is no current, so we can straight away find out the no load voltages as just because of knowing the ratio of the primary and the secondary, right? So this is what is one term. And also there is another term which is important in the industry, which is known as transformer efficiency. Okay, that is P out divided by P in into 100. So we generally tell transformer efficiency in terms of percentage. Okay, so P out plus P loss. Okay, so this loss is because of the I square R losses, hysteresis loss, and eddy current loss. So this is another term. which is known as transformer efficiency. Okay, so that's all for today. In tomorrow's class, we'll take on some problems on transformers also, so that you will get a little more in-depth understanding of the principle of operation of transformer. Thanks a lot for today.